Hello everyone. Let's continue our discussion on the crosstalk glitch example. So we had taken this small circuit, basically an inverter, which was again connected to an inverter, and the net which is present over here, we called it as an aggressor. And we have taken a nearby circuit, a nearby net, which was again connected to two inverters, which was connecting two inverters, two back-to-back inverters, and that net we called it as victim. Let's now try to understand why this is called as an aggressor and why this is called as a victim. Okay. So this particular capacitance is the capacitance between two different nets which are present over here. It's called as the coupling capacitance or the mutual capacitance. So we call it a CM. Let's call it a CM. And this is the capacitance. Basically, you have a quite enough overlap area. This is basically the lateral capacitance that we had talked like some few lectures back. So this is the lateral capacitance that we are talking about over here. So both are on the same layer, both are on the same metal layer, and this is the sidewall capacitance between this net and this net. We talked about all this in the last videos, where we were talking that the lateral capacitance was more dominant. So this is that part. So you have this net which is going in parallel to this net, and we have this coupling capacitance or the lateral capacitance, and let's call it a CM. Okay, so this example is pretty clear now. Now let us draw the other capacitances, which is the grounded capacitance. So basically, whenever this capacitance charged to logic 1, the output of the inverter will be detected as logic 1. Whenever this capacitance discharged to logic 0, or basically the voltage on this capacitor, when it gets to 0, it is referred to the output of this particular victim will be called as logic 0. Okay, so this is the scenario we are taking. We are calling this as an aggressor node, and let us call this as a victim node, and let us call this mutual capacitance or the lateral capacitance between these two nets as the coupling capacitance, and let's call it CM. So now we have to take one case. Let's take this particular case where your aggressor driver input is switching from logic 1 to logic 0. So this is your aggressor, this is the aggressor driver. By the way, this is always called the driver, and this is the load. The input cap of this particular inverter is called as the load, and the one which drives it is called as the driver. Similarly, this will be called as again a driver, and since it lies on the victim side, this will be called as victim driver, and this will be called as victim load. The load which it sees at the input of this particular inverter, that will be called as victim load. Okay, so the case is aggressor driver input is switching from logic 1 to logic 0. So this is the aggressor driver input that we are talking, and this particular driver is switching from logic 1 to logic 0. Okay, that is the first assumption. And the second assumption is victim driver input is at steady state logic 1. So this particular victim driver is at steady state logic 1. So we have a waveform which is going from logic 1 to logic 0 at the input of the aggressor driver, and the victim driver input is at a steady state logic 1. Okay, it is let's say some functionality over here makes it to be at logic 1. So that's why it is at logic 1. Let's try to assume that there is some circuitry which is present over here which wants this particular input to be at logic 1 at this point of time. Okay, so let's put all the case values over here. So we have the logic 1 at the input of the victim. So once we have the logic 1 at the input of the victim, the output should be at a steady state logic 0, ideally, or typically. Whenever your input of the inverter is at logic 1 steady, your output of the inverter will be at logic 0 steady. What does that actually means? It means that this particular capacitors are completely discharged. So at all this node, on this complete victim line, you have a 0 voltage. All these capacitors are completely discharged, and you have a straight logic 0 line. over here. If you try to draw the waveform of it, this will be logic 0 line. Okay, so this is a scenario for the from the victim side. Now let's try to see what happens when we provide an aggressor driver input that is switching from logic 1 to logic 0. We'll look at step by step and we'll see what happens. Okay, so so I think this part is pretty clear that the victim input is at logic 1, victim output is at logic 0. This is very important to understand what scenario or what case are we looking at. That's why a bit repetitive over here. So input is at logic 1, output is at logic 0 constant. Now let's switch the input driver, the aggressor input driver. So when aggressor is at logic 1, aggressor input is at logic 1, aggressor output is at logic 0. Okay, when your aggressor input starts switching from logic 1 to logic 0, after some finite delay, the output aggressor will start switching from logic 0 to logic 1. And finally when the aggressor input reaches to logic 0, the output of the aggressor reaches to logic 1. Okay, so this is pretty self-explanatory waveform that we saw. Now what happens is, when this particular aggressor is switching from logic 1 to logic 0, it sees this particular capacitance. So consider this capacitance, consider this lateral capacitance that we have between this net and this net at, let's say, some bucket. It's a bucket, but it's leaky. It has got a hole at its bottom. So this is a leaky bucket which is placed something like this. So this bucket leaks, and how this bucket leaks is, when this bucket leaks, it throws the water in this nearby net. So for example, we have a tap over here and the tap is open, and when the tap is open, it tries to charge the capacitances on this particular net, and also it also throws some water in this bucket. So basically, whenever we say that it is switching from logic 0 to logic 1, basically it is depositing charges on the capacitor that it sees at this node. Okay, and also the capacitance that it sees at this node, it also sees this capacitance as well, and this capacitance is just like a leaky bucket with a hole, because it is not grounded. So you see two types of capacitance over here. One is the capacitance which are grounded, which are completely grounded, the ideal ones, and there is one more capacitance which are between these nets. So these are not grounded, but it is connected from one net to another net. So let's call it as a bucket, and it's a leaky bucket. So whenever this particular tap is open, it tries to charge all the capacitances. It tries to put water in all the other capacitances which are grounded, and also it tries to put charges, or it tries to put water in this leaky bucket as well. So since this bucket leaks, whenever there is a charging behavior that you see at the output of the aggressor, this particular water leaks and then gets deposited in this particular bucket. So these are other buckets which are now empty, but due to this leaky bucket you see over here, this particular bucket gets filled for certain amount of time, and then it gets discharged. And how it gets discharged, we'll talk about very soon. But this is the scenario that you see. This is the crosstalk behavior that you see. You have a leaky bucket over here. You have the aggressor output that is switching from logic 0 to logic 1. Basically, it means there are some other buckets that it's filling with charges or with water. And while doing that, it sees a bucket which is leaking. And because of this leaky bucket, it tries to also throw water through this bucket onto these buckets. This particular capacitor also tries to get charged, and as a result of that, for momentarily, this capacitors see a rising waveform kind of thing, or the voltage on this capacitors rises from 0 volts to some finite volt, and then it settles down to 0 volt. So there are two things to observe over here. The first thing is that whether this particular glitch, or this is basically called as a glitch. So this particular glitch is a harmful glitch, or how does it affects? Basically, we had learned in the other video, in the previous video, that if this voltage, if this voltage lies less than 100 millivolts in a zero point 0.1 micron and below process, it will be considered logic 0. If this voltage level goes beyond 900 millivolts, it will be considered as logic 1. And if this particular voltage level, lies somewhere in between 900 millivolts and 100 millivolts, so it goes into an undefined region. So basically that's called as a, so this is called as a glitch. And now, how harmful is this glitch, or or whether this particular glitch is even harmful or not, that again, it's a deciding part. That is first thing. Second thing, we have to see, while it rises over here, what is that thing that is bringing it down to 0 volts? Basically, it gets down to steady state voltage. But what is that thing? Basically, it is the inverter that is bringing it down to 0 volts. But we have to see how actually this behavior happens. So this is a very critical or very typical behavior of crosstalk, which becomes a bit difficult to understand if we don't show it without any graphics. That's why we have developed this infographics on crosstalk. So this is how it is. Basically, this is the example that we have been talking about for in order to explain crosstalk glitch. So since this was the first example of its kind, that's why we went a bit slow. Let's try to cover the other parts where we have to see how it gets discharged, how this thing gets discharged. And the second thing, that whether this particular glitch height, whatever height of the glitch that we see, whether it's harmful or it's tolerable. So let's try to look into all this in the next video. Thank you.